Welcome to The Explainer. Today, we're going to completely change the way you think about the future. I mean, from the dawn of civilization, predicting what happens next has basically been the holy grail, right? We want to know exactly what's going to happen and exactly when. Imagine you're a rocket scientist trying to guarantee a successful multi-billion-dollar launch. Or on a much more relatable level, imagine you're just trying to predict the exact score you'll get on an upcoming final exam. In both of those cases, our deeply ingrained instinct is to look for one single definitive answer. We want a perfectly clean number. But what if I told you that looking for a single answer is actually the worst possible way to predict reality? It's mathematically flawed. So today, we're unpacking a massive paradigm shift and how we actually predict the unpredictable.
Here's our roadmap for today's explainer. We'll start with number 1, the problem with certainty. 2, enter Monte Carlo simulation. 3, the 4-step workflow. 4, high-stakes applications. And finally, 5, the pros and cons.
All right, section 1, the problem with certainty. Why a single answer is actually a trap. To really understand why certainty is a trap, we have to expose a foundational flaw in how we think. We naturally crave certainty, especially when the stakes are high, but reality just isn't fixed. Take this exam score analogy. A traditional deterministic model gives you one confident but ultimately hollow answer. It says the student will score 75. It pretends the future is perfectly fixed and ignores all the chaotic variables of real life. But the probabilistic model, using the Monte Carlo approach, tells a completely different story. It says, sure, the most likely score is 75, but it gives you a highly realistic range of 60 to 85. And, more importantly, it tells you there's a 25% chance of getting a high distinction, and crucially, a 3% chance of failing. Why is that better? Well, because knowing you have a 3% chance of failing is actually actionable. It tells you exactly how much risk you're carrying, so you can study a little harder to close that specific gap. One approach is just a rigid, arrogant guess. The other actually embraces the messy uncertainty of the real world.
And this brilliantly illustrates the real-world problem. A normal engineering calculation might simply assume a room's temperature is exactly 20 degrees Celsius. But reality doesn't work like that. Reality fluctuates constantly. The temperature varies randomly around 20 degrees because of things like sensor noise, drafts, changing weather, or even slight manufacturing tolerances in the building's insulation. When you ignore those variations and design a system for exactly 20 degrees, your predictions become incredibly fragile. What happens when the prediction breaks? The HVAC system overworks, crucial mechanical components fail, or the engineering tolerance shatters completely just because the system couldn't handle a totally normal, expected drop to 18 degrees. Moving on to section 2, enter Monte Carlo simulation, the lens of reality. So, how do we fix this flawed way of thinking? Enter the Monte Carlo simulation. By definition, this is a numerical technique that uses random sampling and repeated computation to study systems containing uncertainty, variability, or randomness. It completely abandons the idea of a perfectly predictable universe. Now, you might be wondering about the name. It's actually named after the famous Monte Carlo casino in Monaco. The scientists who developed this during the Manhattan Project realized that predicting the behavior of complex physics was a whole lot like spinning a roulette wheel. It's a game of chance governed by randomness, and recognizing that randomness is the very first step to actually mastering it. Instead of demanding a single, impossible answer, Monte Carlo asks a much better, much deeper question. What range of outcomes is possible, and how likely is each one? That one single shift in perspective changes absolutely everything about how we assess risk. It moves us away from blind guessing and right into computed probabilities. But here is the real secret to why it's so incredibly popular across every major scientific field. It actually makes the math easier. Seriously, many real-world systems are incredibly complex, driven by closed-form mathematics. For most of us, that means equations so massive and so deeply entangled that they take a human a lifetime to solve on a chalkboard, if they could be solved at all. Monte Carlo bypasses those impossible equations entirely. Rather than trying to elegantly solve for x, it relies on brute force statistical sampling to map out reality.
Okay, section 3, the 4-step workflow. How the simulation engine runs under the hood.
The simulation engine runs on a really basic 4-step loop. First, we define the uncertain inputs. Second, we randomly sample those inputs. Third, we run the model repeatedly. And fourth, we analyze the statistics. Now, while these 4 steps might sound simple on the surface, their execution is incredibly powerful. Let's break each of them down. Step 1 is where we literally acknowledge what we don't know. We list our uncertain inputs. In a complex machine like a spacecraft, for example, this could be thrust uncertainty, a slight bias in a navigation sensor, unpredictable atmospheric orbital drag, or tiny, microscopic clock errors. Instead of assigning a single fixed number to these factors, we assign a probability distribution to each one. Essentially, we map out the boundary of our doubt. We tell the computer, hey, the thrust will most likely be 100, but it could dip to 98 or spike to 102 depending on the conditions. We mathematically define how these inputs are likely to fluctuate.
Now, check out what happens when we look at individual runs in step 2. The computer takes those carefully mapped distributions and randomly samples slightly different inputs for every single run. In run 1, the thrust is 102 newtons, and sensor noise is 0.03 degrees. But on run 2, the roulette wheel spins again. The thrust drops to 98.7 newtons, and the noise jumps to 0.08 degrees. Every single run creates a slightly different, mathematically possible alternate reality.
Which brings us to step 3. You don't just run this twice. You run it 1,000 times, 10,000 times, or even 1,000,000 times. This is the brute force computational power of Monte Carlo. You are literally simulating 1,000,000 alternate realities to see what happens in every possible combination of variations. What used to be entirely impossible for a team of humans to calculate by hand can now be run on a modern computer in an afternoon, mapping out millions of possible futures in the time it takes to grab a cup of coffee.
And finally, in step 4, you analyze the outputs of those million runs. This massive collection of data reveals the true average behavior of the system. You get the standard deviation, which tells you exactly how wild the swings and outcomes are, and the confidence intervals, which basically act as your mathematical safety nets. And most importantly, you find out the exact probability of worst-case scenarios, like a complete mission failure. As the number of simulations goes up, your statistical estimate becomes incredibly robust and incredibly accurate.
Section 4. High-stakes applications. Predicting the unpredictable in the real world. So we understand the theory, but taking this 4-step engine out of theory and applying it to multi-million-dollar engineering problems is where things get truly fascinating. Because real systems inherently contain uncertainty, decision makers who really care about reliability rely entirely on this methodology. You'll find Monte Carlo simulations running the show in aerospace, defense, finance, AI systems, nuclear engineering, and the design of autonomous vehicles. And this matters to you directly. The safety of your retirement funds, the stability of your city's electrical grid, and the braking system on that self-driving taxi you might take next year are all governed by this exact math.
Take Global Navigation Satellite Systems, or GNSS, for example. The signals your GPS receives always contain random noise from the atmosphere. By simulating those random measurement errors over and over, engineers can observe the distribution of position errors. This lets them estimate the true root mean square positioning error, which is just a highly accurate measure of exactly how far off that little blue dot on your phone really is from your actual location. It also calculates the integrity risk, identifying the actual probability that your navigation system will completely drop out when you need it the most.
Or consider space mission design. When you launch a rocket, the injection error varies, propulsion efficiency varies, and sensor noise varies. By running a Monte Carlo simulation, scientists aren't just guessing, they are accurately estimating the actual probability of reaching orbit. They can calculate the real fuel margin risk, because, let's be honest, running out of fuel in the vacuum of space means a multi-billion-dollar mission is dead in the water. Ultimately, this allows them to determine the true mission success rate before the spacecraft ever leaves the launch pad.
Let's wrap things up with Section 5, the pros and cons, the trade-offs of simulating reality.
We really need to ground this concept. While Monte Carlo is an incredibly powerful tool, it isn't magic. It's a computational method, and like all methods, it comes with specific trade-offs. First, the advantages are immense. It handles uncertainty beautifully and naturally. It works for highly complex systems where traditional math just completely fails. It's incredibly flexible across different industries. It produces realistic, probabilistic results that managers can actually use for risk analysis. And computationally, it's very easy to parallelize. That means you can split those million runs across hundreds of separate computer processors simultaneously to get years' worth of math done in mere seconds.
But you've got to contrast those computational benefits with some critical limitations. Simulating 1,000,000 realities does require massive computational time and power. Plus, your random sampling introduces its own statistical noise. But the biggest limitation is this: accuracy depends entirely on your input assumptions. If you create poor probability models for your inputs, the simulation will confidently produce totally misleading results. It's the ultimate example of garbage in, garbage out. No amount of supercomputing power can fix a human engineer making a bad guess in step 1. The model is only as smart as the boundaries we set for it.
But when done right, the clarity it provides is unparalleled. Consider predicting spacecraft battery life.
Instead of a single, risky guess that the battery will last exactly 5 years, Monte Carlo gives you the truth. It reveals a 70% chance it lasts more than 5 years, a 20% chance it lasts 4 to 5 years, and a 10% chance it dies in under 4 years. For anyone managing risk, having this detailed map of probabilities is just infinitely more useful than a single deterministic guess that leaves you entirely blind to a worst-case scenario.
We've seen how ignoring variability leads to massive blind spots, and how embracing random sampling allows us to literally compute the odds of the unknown. So I'll leave you with this. In a universe intrinsically ruled by randomness and variability, isn't it time we stopped pretending the future's fixed? Take this probabilistic mindset into your next complex problem, and you might just find that embracing uncertainty is the clearest path to the truth. Thanks for joining me on this explainer, and keep questioning the numbers.